Since Galileo built the first telescope back in 1609, observations of the sky have provided an ever more detailed picture of our universe. In the last decade, the Hubble Space Telescope, launched by NASA and ESA in 1990, has looked further into the universe than was ever possible before, unveiling a history of black holes and colliding galaxies. Through Hubble, we discovered that the universe expands at a different rate than we previously thought. But there are still huge gaps in our knowledge of the early phases of the universe. Following the cataclysmic early phase of the Big Bang, the universe slowly cooled over time. With cooler temperatures, stars and galaxies eventually started to form. After about 500 million years, the earliest stars sent out rays of light, bringing to an end a long period of darkness known as the Dark Ages. Over time, the continuing expansion of the universe shifted the light from the first stars and galaxies beyond the gaze of today's telescopes into the infrared band of the electromagnetic spectrum.
Because of the redshift, because of the fact we're looking so far back in time at objects which are receding from us at such great speed, all this light is shifted into the infrared part of the spectrum. So, if you like, we have to chase these extremely faint objects into the infrareds.
Within the next decade, NASA, ESA and CSA will launch the Next Generation Space Telescope, which will be designed precisely to observe a wavelength range from the visible to the mid-infrared part of the spectrum. NGST will have a mission to detect those distant, first-ever luminous objects. Observing infrared light is not easy, as the Earth's atmosphere absorbs most of the infrared radiation from space. Also, all objects in the universe emit infrared light, including the Earth's atmosphere and the Sun. For this reason, NGST will be placed at a location known as the second Lagrangian point, 1.5 million kilometers away from the Earth. This remote location will also be extremely cool, an important requirement.
Well, one of the requirements for a telescope which works in the infrared part of the spectrum is that the whole structure has to be extremely cool, because a warm telescope would radiate the kind of radiation that you were trying to detect, and that radiation would be much stronger than the radiation from the distant source. And so we have to cool the whole telescope to very low temperatures, around -240 centigrade.
NGST will carry a huge solar shield about the size of a tennis court, which will cast a permanent shadow over the telescope, allowing highly sensitive detectors to function properly. The shield will include solar panels to provide electric energy for the telescope, plus a communications antenna pointed at the Earth. The weight of NGST will only be a quarter that of the Hubble telescope, yet its light-collecting power will be 10 times greater. The telescope into space and its mirror will then open in orbit like a flower. Fully assembled, it'll be 6 meters wide, but with a surface density similar to that of a coin. Early stars and galaxies are the fossils of the universe. NGST will be the first telescope able to examine the original stars which illuminated the cosmos, and produce the heavier chemical elements necessary for the emergence of life.
We expect Hubble to remain in orbit for about another 9 or 10 years, and NGST is being designed effectively to take over from Hubble, the son of Hubble, if you like. And although it sounds a rather long time, 7 or 8 years to go into orbit, there's an enormous amount of development work to do on the instruments and the telescope itself. And so we're running to a very tight schedule, but we do expect to have NGST in orbit around the time that we stop operating Hubble.
After launch, the NGST will have another mission. In addition to the study of the most remote galaxies, NGST will also study what is known as dark matter, which scientists believe 90% of the universe is made of. This dark component of the universe is invisible to telescopes. In this way, NGST could further our understanding of what forms dark matter. The average density of dark and visible matter in our universe is the key if we are to understand the final fate of the universe. Will it expand indefinitely, or at some point in the distant future, will it collapse?